people are doing molten weld pool optimization, also molten weld pool prediction, the equations and the temperature sensors also are there. So advanced approaches like many people are using compressive sensing, IoT based monitoring, machine learning integration, all is done in this molten pool. So if we can control this molten pool, our expectation is to that the final product will be very good if we can optimize this thing. Coming to the quality management, if we are doing quality management, VAM faces challenges like irregular temperature distribution that I told you earlier, like temperature gradients, mismatch of temperature gradients, heat input, high heat input problem is there, poor surface finish is there. So these defects are common defects in VAM. So quality management relies on melt pool to predict and avoid the defects. So if we can control the molten pool, we can predict avoid these kinds of defects. So machine learning helps access surface roughness and quality. So if we are integrating laser sensor data, that also improves the surface roughness and quality of the product. Coming to the result prediction. The result prediction, different materials and parameters affect part geometry, repeatability, and defect occurrence. So process simulation, that is the thermal cycle prediction are used, but complex to model. So these things has to be process simulated, then only the result will be, the result output of the VAM component will be very good. So digital twins and machine learning is the integrated part. So if we can make these pillars strong, like digital twins and machine learning, these two influences and optimize this process, pre-design this thing, and fabrication control, both can be optimized by uh, using digital twins and machine learning. Okay, so coming to the process model delivers 1D spectrum, 2D image, and 3D tomography. So basically 1D data is like current, voltage, wire feed, welding speed. That is the simple and low cost but limited information can be driven from that. 2D data is industrial cameras, photodiodes, laser scanners, X-ray imaging, captures, surface topography. So many things are there for 2D imaging. And coming to 3D data is point cloud inspection, XCT imaging. So that allows non-destructive evaluation of internal structures and defects. So this can be done after fabrication. So if we can make 1D, 2D, 3D modeling and 3D tomography, so we can get the information about the defects, what are the defects inside the VAM component, without like it is a non-destructive way of getting the defects. So we can get the quality, how what is the quality of the VAM product, and then we can improve that quality after, like if we have the feedback, we can improve the quality for the final part. So this is the final part delivered. Going to the next slide. So this is the selection of process parameters during VAM. Sorry, process parameters like welding current, speed, wire speed, shielding gases. These are the process parameters you can take. Yeah, sorry. Then product quality is geometry and dimensions, surface quality, physical properties, mechanical properties. These are the product quality. Process signatures that I told you, that molten melt pool, flow field, residual stresses, grain growth, that can be optimized. Then post processing is by residual stress release, heat treatment, post machining, and short peening can be done by improve the quality of the VAM product. So this is the basic schematic VAM representation on CMT with path strategy. One second. Yeah. So this thing is the base metal, substrate metal, and this thing is the number of layers that is implanted. So substrate metal, one layer over the other is made. This is the building direction that is given this side. These are the path strategy that is adopted, and this can be optimized also. In this schematic diagram, I've taken like bi-directional strategy. So from A point to B point, then deposition start from B to A. So alternatively, we are doing. So this is called the bi-directional strategy. This is a single track, single wall structure component. That's why only we are doing for the path strategy. So we can use bi-directional. For multi-wall or multi-track, we have to adopt different path strategies. So this is for single track and single wall structures. So here the CMT, this thing is there. DCEP reverse polarity we are using. Wire movement is this. The steel liner is connected. Steel liner, basically, if we use a hard material steel wires, then we use a steel liner. Otherwise, if we are using softer materials for fabrication of a WAM component in aluminium, magnesium, softer materials, then Teflon liner is needed. So these liner has to be changed according to the material. This is the wire feeder. This is the wire buffer. Wire buffer is having an important function in CMT, that the wire has to be retracted. So this wire buffer retracts this wire. This wire has been retracted as the short circuiting transfer, metal transfer takes place. So as the droplet is just touching the molten weld pool, when it is just touching, the short circuit happens and the wire is retracted. So it happens like almost 60 to 70 times in a minute, in a second. So it's very rapid. It's not visually seen. Through the CCD camera and slow motion cameras, we can we can check in the milliseconds how much, like 60 to 7 times it is retracting in a single second. So this is very rapid motion. So that's why it is known as low heat input welding machine, because as the wire is retracted, the droplet is detached. So the reason for droplet detachment is the retraction of the wire. So wire is retracted, so droplet is detached, and it is very different from the conventional GMAW process. Conventional GMAW process is having the Lorentz forces responsible for this droplet detachment, but for CMT we have the wire buffer. We have the wire retraction motion to draw to remove this droplet into the molten pool. So wire retraction motion is important in CMT. So because of this, the droplet that is detached is having low current and low voltage. At the time of short circuiting, the current and voltage in the current waveform and the voltage waveform is reduced in the CMT as compared to GMAW. So as the current and voltage is reduced at time of short circuiting, you can see like this droplet is detached to the molten weld pool at the very low heat input. So as compared to GMAW, it is almost two-thirds of the heat input can be achieved. So one-third of the heat input can be reduced easily. So this is the cross-sectional image. If you can see in this image, this is the cross-sectional view, magnified cross-sectional view of this area. So you can see this is the first layer, this is the first layer, this is the second layer L2, and L3 is the third layer. So as the layers are increasing, in between the two layers, there is the inner layer L12, and the layer between 2 and 3, there is a L23. So L1, L2, and L3 are the normal layers, interlayers, and L in between the two interlayers there is one layer forming as inner layers. So L12 and L23 are the inner layers. That is, you can also call it as heat affected zone. So this is the weakest zone of the WAM process. Weakest, this is the weakest portion. So the globular grains can be formed. So that's why, to improve the WAM quality, we have to improve this area. We have to improve this inner layers. So if we can if we can like first layer and second layer implantation, in between the temperature is kept constant throughout the building direction. throughout the building direction, if the temperature is kept constant in between every layer, then many researchers and we also uh, we have experimentally done that, like if we can keep like temperature 200 degrees Celsius in between every layer and throughout the component, if the temperature is constant, then the properties are enhanced and the this weakest zone is not that much weak, like the grains are modulated and like it is transforming into a columnar or any quiax grains. So it depends on the how well we are fabricating the component. If we are having the thermal imaging cameras, the other temperature sensors, we can integrate and we can fabricate a very good VAM component through wire archive manufacturing using CMT. So going to the next slide. So basically, this VAM, why VAM is important as compared to other welding, other additive manufacturing is like laser powder bed fusion, extrusion based additive manufacturing. There are many additive manufacturing techniques, but why VAM is preferred? Because it is having high deposition rate, it is very economical, and it is having shortened lead time. Like for a less time, for during less time, we can fabricate a bigger component and higher because of higher deposition rate. Like it is almost 3 to 4 kgs per hour. This much high deposition rate we can achieve. It is very comparable to GMW because it's an advanced version of GMW. So GMW is also having high deposition rate. So CMT carries the same thing from the parent process, and it is very economical. It's not that much costly as compared to lasers and other complex process. So large scale metallic components with moderate complexity can be achieved, and near net chip product can be formed using this. So coming to the basics, GMW is the basic parent material parent process of CMT, and CMT is the advanced version of GMW. So basically, GMW, everyone will be knowing about this. It's happening a conventional short circuiting transfer. Lorentz forces is basically uh, important, or Lorentz forces are the responsible factor of detaching the droplet from the wire to the molten pool. So Lorentz forces means like electromagnetic forces, the gravitational forces are the forces that is uh, giving the extra push to the droplet towards the molten pool. So this pinch effect is seen in this GMW. So this is the basics of GMW. So how we can transform GMW to CMT? So that is made in 2004. Fronius company has made. So that is of Austria company. So it's like it doesn't mean it's cold. Like it's and the name is known as cold metal transfer, but it doesn't mean it's cold. It's comparative. Like the terminology is in it's a comparative standard terminology as compared to GMW. Like if we are having um, like 1,000 kilojoules or 1,000 joules of energy is used in a specific work with GMW, CMT will be doing that same work, same process with same process parameters, same controllable factors with a lesser heat input like 660 or 650. So it's achieving almost two-third of the heat, using two-third of the heat, and the you can see with lesser heat input, the quality of the weld or quality of the product is higher. So the thermal problem won't be having major issues in this CMT process. So as the word suggests, cold means this is only fusion welding technique that has a very low heat input due to very low non-zero current. So why this heat input is very low? As I have told you earlier, during the short circuiting transfer, the current and voltage waveforms are reduced as compared to GMW, that I'll show in the later slides in the current and voltage waveforms. So CMT provides controlled method of material deposition and low thermal heat input by incorporating an innovative wire feed mechanism coupled with high speed digital control. So there is a high speed digital control which controls this wire mechanism. This is the wire here, the wire buffer, and this is the digital process control, DPC. So DPC is the heart of the CMT machine. So this controls everything. This controls the filler wire, how at what time the filler wire has to step back or make a oscillator motion. So that is done by the digital process control. At the time of short circuiting, it is controlling. So liquid droplet detachment forms filler wire from filler wire is due to wire retraction motion, which gives better arc control. So this is the concept of CMT. You can see in this file, the arc length is constant. One second, I'll show you again. The arc length is constant, but the wire is retracting. So it's very fast forward. This image is captured from a slow CCD camera. So this is recording in milliseconds. So that's why we can see the retraction motion of the wire that much quickly. So this is the CMT process. So we have, the process is arc ignition, short circuiting phase, then retraction of wire. So after arc ignition, the wire pulls forward towards the workpiece, and then at the time short circuiting happens because the filler wire just touches the molten pool. The filler wire or droplet just touches the molten pool. As it is touching, the retraction of wire is taking place, and this process continues again and again. So this is the one cycle of CMT. So how this temperature and current and voltage waveform happens, this can be measured by oscilloscope. If we are integrating oscilloscope sensors in this welding machine or CMT machine, so we can get this current and voltage waveforms. We can track down how, at what second, at what milliseconds, with how much current was there, how much voltage was there, we can easily measure. So this is the process, that is peak current phase is the first current phase in the CMT process. Then it is background current phase, this is BCP, and then SCP, that is short circuiting phase. So in PCP, that is high pulse of current is given for a shorter duration. You can see here, for a shorter duration, only this second, only this much second, this high peak current is given. So at a shorter duration, high pulse of current is given. So this is given, why? Because to melt the electrode wire to form a droplet. So just we are giving the high intensity of current to just form a droplet, to form a droplet. Okay. Oh, then the BCP, that is background current phase. The you can see in the current phase diagram, the background current phase is reduced as compared to peak current phase. The current is reduced. So this is important to lower the current phase to prevent globular transfer. So if we are not controlling the current, because if we are not controlling the current factor, or if it is almost till the peak factor, peak current phase, so if that is around this much, though, then the droplet will be increasing, and it will increase to a globular transfer. So that we don't want. As the globular transfer is happening, the spatter generation will be more and heat input will be more. So what CMT is good at, like after peak current phase, the current is suddenly dropped. It is suddenly dropped to prevent that. At this point, the droplet is already formed. As the droplet is already formed, the current is suddenly dropped, and the droplet shape is maintained, or it is not a globular, it is a very tiny liquid metal. So as this very small tiny droplet is splashing into the molten pool, it is having no spatter generation. You can imagine like throwing a uh, big stone in a pond, or throwing a small stone in a pond. The it is the example given by Fronius only, like throwing a stone in the pond, like a small stone or tiny particle. So the spattering we can connect from that, the spattering will be very less as compared to GMW. So GMW doesn't prevent globular transfer, and it is You have also done GMAW process. That's a basic UG courses we have done. So in GMAW, we are very much seen that around the welding there are very much spatter generation. So in GMAW there is no controllable factor. So in but CMT is good at controlling the current phases. As it is controlling the current phases, spatter generation is very less, and we can achieve a tiny droplet. So as the droplet is just touching the next current phase is short circuiting phase. So after the background current phase, the short circuiting phase is this one. It is not that much high. The current is almost less, and you can see the voltage transformation. Voltage is suddenly dropped. It is almost negligible, zero voltage at the time of short circuiting. So at the time of short circuiting process, it is achieved zero arc voltage. Wire comes in contact with the weld pool. Wire retraction mechanism by digital process control is done. As it is just touching the molten weld pool, the wire is retracted. You can see here, wire is retracted, and only tiny droplet is detached. So as it is detached, no spatter generation is there, and droplet detached and deposited. So this is the complete process of CMT in detail I have discussed with you. So this is the pulse current phase, then background current phase, and short circuiting phase. All this combines to a process that is, and you can measure this current and voltage transformation through oscilloscope through CMT. So this is a controllable factor by CMT. And you can see the main differences. The main difference between GMAW and CMT is GMAW conventional short circuiting transfer, and this is advanced short circuiting transfer. You can see in the waveforms, this is the waveform for GMAW and this is the waveform of CMT. You can see at the time of short circuiting, this is the time of short circuiting, the voltage, this is V voltage and this is current. So voltage and current both are increasing. So this is not acceptable for less spatter. So this will having a spatter, more spatter thing, bigger, heavy spattering, and the droplet is also forming a globular transfer, and the droplet when it is detached, so the more heat input is given, because heat input formula we are well known like eta Vi by S. So as heat input is directly proportional to current and directly proportional to voltage, the heat input will increase at the same process parameters. Okay, so at the time of CMT, the digital process control, which automatically detects the short circuit and helps to detach the droplet by retracting of the wire. So liquid droplet detachment from the filler wire is due to wire retraction motion. Drive mechanism in the welding gun oscillates the wire. This to and fro motion, this oscillation motion from the workpiece provides the foundation of the better arc control. So there are many characteristics that are very well designed in the CMT as compared to GMW. So that's why researchers are adopting CMT as a power source for fabricating additive manufacturing component, like for wire arc additive manufacturing. People are adopting CMT as compared to GMAW. So that because of these characteristics. So you can see some practical thing that I have done here. Pros and cons of GMW. It is conventional short circuiting transfer. You can see fast process. It is fast process. Higher thickness can be welded or higher thickness can be made. And the cons are high thermal heat input, over penetration, cracks, high spatter, heavy distortion. So these are the problems caused in GMAW. You can see here at 120 ampere, the MIG manual. This is the GMAW process, and the same process parameter. This is shown over penetration. So 120 ampere and 7.5 mm per second travel speed on a 3 mm plate thickness. You can see an over penetration with the GMAW process, but the same thing achieved by CMT with 120 ampere current and the other same speed also, the welding, there is no over penetration, thermal heat input is very less, and you can see here at this same current the cracks are formed in the GMW process, but here no cracks are formed. It's a very good weld bead. So you can see the differences. And the third one difference is burn through. You can see with GMW there is 3 points there we have experiences the burn throughs by joining these thin sheets, and you can see with CMT no burn throughs are there. And you can see this is the very big problem in GMW. As the heat input is high, then what happens to the thin sheets? You can see on the screen like it is distorted completely. So by increasing the heat input, these problems will happen. For example, if we are making thin sheets, fabricating a single wall structure, GMW is not well suited because the distortion problem, the high heat input problems are there, and then anisotropy problems will be increasing, the staircase defects will be increasing. So these defects is increasing by using GMW process. So an advanced version is better opted for WAM. So CMT offers spatter-free weld, very low thermal heat input, high gap bridging ability, negligible distortion. These are the benefits of CMT. So we will be this completes the CMT processes. How CMT is made, or how CMT process is used in the fabrication process. So next is integrating, how we are integrating smart manufacturing in additive manufacturing. So these are the these are the seven main things, main processes. First is process monitoring and control. So how process monitoring and control affects the quality of additive manufacturing. Then digital twins and simulation. Then data analytics and machine learning. Then industry 4.0 integration, automation and robotics, sustainability and resource efficiency, and mass customization flexibility. So these are the seven important things that helps additive manufacturing to be a smarter product, to fabricate a smarter product, or uh, influencing smart manufacturing in AM. So first is process monitoring and control. So process monitoring and control happens to be very important concept because it has a real-time sensors like vision, thermal, acoustic monitoring, many other sensors are there. And then we have defect detect. It detects the defects like porosity, warping, bead irregularities, and these defects can be detected by process monitoring. And then closed loop control ensures stable and consistent deposition. So closed loop monitoring has to be done to derive the data, or we have to collect the data and then monitor that data, and uh, then give a feedback, good feedback for the good product. So these are the real time sensors. Sensing technologies are, so optical sensors like cameras, infrared thermography, acoustic sensors, acoustic emissions, and sound monitoring, electrical signals like arc voltage, current fluctuations, other methods like X-ray CT, ultrasonic sensors. I'll be discussing all these. So defects in WAM, there's a common defects like porosity, lack of fusion, surface roughness, cracks and distortion. So these are the basic defects. Yeah. So this is the schematic of defects and examples of sensing technologies I've taken from one recent paper in WAM. So you can see all the things. First of all, WAM is we all know it's an additive manufacturing process derived from automated welding, offering higher deposition speed, material efficiency, reduced cost compared to other AM technologies. We have already discussed CMT as an alternate, as a best source, as power source as compared to other processes. So despite its advantages, VAM faces unique challenges beyond welding. Beyond welding, VAM is having other challenges also. Not welding is a major challenge, but we have by choosing CMT, we can reduce that challenges for the welding part. But apart from welding, there are many unique challenges like including oxidation, geometry irregularities. Geometry irregularities are the major problem in VAM because when the bead profile we are putting like layer implanting layer by layer, the side on like the side wall will be having a surface roughness, higher surface roughness. So we have to do machining part for the VAM components because we can't use we can't have a near net shape product. Like slight machining has to be done. It's a like hybrid manufacturing we are doing. We are doing an additive and subtractive manufacturing. So the geometry irregularities are the main defect. Like if we can control that things by using different sensors and other things, then it is like reliable, like we can fabricate a near net shape product. So that is also a major problem. Then other problems beyond welding are uncertain substrate temperature. So substrate temperature should be also consistent. Then residual stresses are major problems. Then small processing areas, high sensitivity to defects. So these are the major problems. So common defects, I've already discussed the cracks, pores, inclusions, lack of fusion, delamination. Delamination is also a big problem if we choose a lesser heat input process parameter that is having a very low dilution. If the dilution of the bead is very low, then it is easy that the layers can be detached from each other. So this happens in the similar welding. But if we have like if we have to fabricate a bimetal component, suppose aluminum stainless steel. So if we are implanting one layer of aluminum and implanting the second layer as of the different material of stainless steel, so that is having also a problem because of different thermophysical properties of stainless steel and aluminum. And the stainless steel dilution in the aluminum won't be that much, or aluminum dilution.
सर आवाज नहीं आ रही सर आपको स्टॉप शेयरिंग
Similar or dissimilar materials, but we have to infuse two layers, but in a correct method. So if we are forming the two layers, we have to make the uh, deposition correctly, and the temperature should be maintained. Otherwise, these delamination problem will be very much. Okay. So defects causes includes environmental factors, that is poor shielding gases, process issues, unstable arc, improper wire feed, incorrect parameter setting, for instance, like porosity. These are the defects that is normally in VAM we are experiencing. Porosity caused by hydrogen gases, unstable gas flow contamination, delamination, lack of fusion due to low heat input. Delamination is due to low heat input or energy input. Delamination that I've already discussed.
सर
Geometric
आपका
deviations. Hello.
स्क्रीन नहीं शेयर हो रहा स्लाइड शेयर नहीं हो रही सर
Slide 1 second. Now it is visible.
नहीं सर
1 second, 1 second. Now it is visible.
यस सर
Okay, it is visible now.
यस सर
Yeah, yeah. So the other defects like geometric irregularities or geometric deviation that is formed that is from high energy heat input and unstable arc. So unstable arc and high heat input are the main causes that forms many defects. So if we can control these things, we can get a very good product. Then residual stresses is also a problem that leads to distortion, cracking, and delamination also. So to improve these things, so to improve these defects, what we have to use, so what we are adopting the techniques by smart manufacturing is optical sensors like spectrometers, cameras, visual sensors, then acoustic sensors like microphones and charge sensors, then electrical sensors like current and voltage monitoring, and thermal sensors like infrared cameras, infrared sensors. So recent, like you can see here in this optical sensors, what we are using, then acoustic sensors, current and voltage sensors, vision, thermal imaging camera, how we are connecting the other sensors like ultrasonic sensors, then laser assisted ultrasonic sensors can be used. So these all sensors can be used to get the feedback, the actual feedback, what is happening during the fabrication, or what is happening what is happening in during the droplet detachment and the fabrication process. So what actually because we are not knowing what the actual fabrication is done, or how the actual fabrication can be done, but by these sensors and the collected data we can analyze the data, and then we can optimize these things to and integrate these things to form a better product. So recent research emphasize multi-signal fusion. Fusion like combining acoustic and electromagnetic or vision and spectroscopy. So multi sensors are also used for more reliable monitoring. Machine learning, especially deep learning, is applied to process the collected data, enabling defect detection, process monitoring, and closed loop control. So multi sensors also can be used to get more reliable data. And then machine learning, already we have this machine learning to optimize the big data and these things to especially deep learning to enable defect detection, process monitoring, and these things. So next next we this is the examples of optical sensors based sensing systems. So you can see the CCD spectrometer is used for the optical sensors, optical signal based sensing, and NIR spectrometer. So optical sensing technologies, mainly using spectrometers and optical fibers, are it is widely adopted and monitoring welding and VAM process. So it's a very common thing, but these sensors, if we integrate, we can get the optical data. So these provide non-contact, real-time, and cost-effective defect detection, particularly for porosity, lack of fusion, oxidation, and surface contamination. So these things we can we can get the real-time data for these things. So the CCD spectrometer that is attached here. So these spectroscopy detects porosity, low welding current, lack of shielding gases, oxidation, and penetration issues. These can be made by this. It works by analyzing plasma emission radiation from the electric arc, and the advantages for this spectroscopy is that is real-time data can be detected, and limitations for this is the accuracy challenges, difficulty in detecting minor defects like very small porosity can be missed out from this. Yeah, grain size, smaller grain size like fine grain size or very small porosity can't be detected. So this is the problem for this. And there is photodiodes also. So photodiodes detect plasma, vapor plume, reflective laser energy, and thermal radiation. So these are the optical signal sensors. So what are the strengths of basically why we are using it? Because it is why we are using optical sensors is we are getting a non-contact real-time monitoring data, high sensitivity during welding, effective for porosity. Because why we are using? Because we need a good real-time data for porosity, oxidation, penetration, spatter, and contaminants. So these things can be analyzed, and we can change the process parameters or to optimize the process parameters. These data are very helpful. So it is less affected by environmental compared to X-ray or ultrasonic testing also. So this completes optical sensors. So coming to acoustic sensors, I think time is there. We can finish this slide, and the later slides I have two sessions also in the evening. I will be continuing this PPT so that you can see. So this acoustic sensor I will be explaining. So acoustic sensors for VAM and welding mainly uses microphones and acoustic emissions, that is AE sensors. These devices capture sound or vibration signals from the arc or workpiece to detect from the arc also. This from the arc the vibrations are to be calculated, and from the workpiece also. So from both the sides the vibration signals are to be captured, and to for defect detection and process instabilities, these are very helpful. So advantages of microphone based detection is it is low cost, easy installation. It is strongly correlated with weld pool vibrations. So weld pool vibrations, these microphones are very strong capturing of vibrations, so that is very helpful. So the problem for this microphone based detection is it is highly sensitive to environmental noise. Suppose if we are doing the welding, the environmental noise are too much, in that if the welding machine is not kept in the closed environment or in a clean room or a specialized welding room, then the problem of microphone is that it captures the environmental noise also, so that is not needed. So that has to be that is the problem using microphone. So it should be like if we are doing the fabrication process, we have to do in a very specified welding room or a similar to a clean room system we can generate. So it is highly sensitive to environmental noises, requires careful position to avoid spatter and radiation also. So the application of microphone is like detects incomplete penetration, that misalignments, porosity, spatter, and line width deviation. It is used in laser welding also, and GMAW, CMT, everything, everywhere microphones are used, often mounted on robot arms or near to the torch. So you can see here microphones is near, this microphone is very much near to the torch. So the positioning is also important, how because if we keep this microphone too much far, the vibration signals are not that much strong that it can detect. So it should be very close to the torch. It should be very close to the torch, or uh, in the that range of the microphone. So and apart from microphone, there is AE sensors. So AE sensors, it captures high frequency transit acoustic waves, that is zero point 0.1 to 10 megahertz frequency it can take, or 50 to 400 kilohertz in some cases. There's the special cases. So the high frequency transit data that can be easily captured. So the advantages of using AE sensors are like it is better for studying weld stability and detecting internal defects. So internal defects can be detected, so you can use these sensors. Less effective by audible noise. So compared to microphone, AE sensors are very good. Environmental noise it can remove. and the application part is like it is application for AE sensors are like defect it detects slag, porosities, cracks, burn through, and under penetration can be mounted on the fixture or plate to capture emission traveling through air or material. You can see here AE sensors is connected to the plate itself here, and in the practical image also, this is the plate and AE sensor is attached to the plate itself. So as much close as the substrate plate it is attached, the better or reliable data you will achieve. So multiple AE sensors also you can use with different frequency ranges that can be combined for broader detection. So these can improve the quality of WAM component. So we have completed optical sensors and acoustic sensors. So I think the time is there. Time is there, Vishal.
No, sir.
So
Because our
after this, we can continue after like 4:30 to 6:30. I'm having 2 hour session, so I can complete these things.
no, sir. The participants, our next speaker is Dr. Dhanesh G. Mohan. He will deliver his lecture within few minutes. So thank you very much, sir, for this insightful session.
Yeah, if there isn't any question, like I can take in the evening session 4:30 to 6:30, so I can take the questions at that time.
Okay, so participants, you can put your questions in the chat box. Sir will cover your questions in evening session. Thank you.
Thank you, Vishal. Thank you.
Thank you, sir. Uh, Dhanesh, sir.
Yeah,
Hello,
I'm here.
sir. We are audible.
Yeah, it's audible. I'm just
Can you?
checking. There is some. I want to share my slides with you. Mm, in this showing is some restrictions. Let me check it. Give me a moment, please.
Sure, sir.
Mm, I don't know what's happening.